Hello, lesson 2, plate tectonics. This lesson will be about plate tectonic theories that go towards explaining why plates are moving and the evidence to show that plates are moving. So, what we're going to learn then? Yeah, the theory of plate tectonics, its key elements and processes. A little bit of a recap, as to why it's important, because these processes will cause as tectonic hazards at different type of plate boundaries. Alright then, so just a little bit of a recap. Last lesson we looked at how we get we looked at the distribution of tectonic hazards such as earthquakes, volcanoes and tsunamis, and we realised that if we map them, we find the vast majority of volcanoes and earthquakes are found near or on plate boundaries. Alright, and the most severe volcanoes, volcanic eruptions and high magnitude earthquakes are found at destructive plate boundaries, like on the Pacific Ring of Fire. And we found low magnitude earthquakes and volcanoes at divergent or constructive plate boundaries, and the orange, which is conservative plate boundary, we find only earthquakes and no volcanoes. Alright, and I've just put a couple of graphics to show the three different types of plate boundaries. So this one, we've got a mid-ocean ridge where magma rises, and as soon as it breaks through the surface on the ocean floor, it cools and sets as new rock. This is also known as a constructive plate boundary or a divergent plate boundary. Alright, so we find volcanoes and low magnitude earthquakes at this one. Destructive, where one plate subducts under another plate, is where we get our higher magnitude earthquakes and more explosive volcanoes, like on the Pacific Ring of Fire. And the conservative plate boundary, where plates are sliding past each other, we get medium to high magnitude earthquakes, but no volcanoes. That's important. The reason why we get medium to high magnitude earthquakes is because the earthquakes' focus tend to be really shallow, so it tends to be nearer the surface. Alright then. So, strap yourselves in. How do we know all this? Right, well, we need some kind of... there needs to be some kind of theory. So, Mr. Wegener, Alfred, this is the geezer, just here, 1912, he looked at a world map, so we'll go through the process that he went through, and observant, he noticed that the continents tend to fit together, or the coastlines and major landmasses tend to fit together, broadly speaking, like a jigsaw piece. So you can see, look, South America and Africa, if you move that South America to the east, it slots into Africa. Same with kind of North America. If you moved it towards the west coast of Africa and Europe, it tends to fit together. Yeah, I mean, it is very kind of broadly speaking, but it thought, well, these coastlines have been eroding, there's been processes acting on them for hundreds of thousands, even millions of years. I think once upon a time, these continents fitted together. They were all one continent. That was his theory. Now, a theory is an idea, and until it's proven and you've got evidence, then unfortunately, that's all it is. It's a theory or a hypothesis. So this was Big Alf's theory, right? He thought that the continents once fitted together, and he called this supercontinent Pangea. But he needs to prove it, so evidence then to support Wegener's theory: land-based fossils found on kind of adjacent continents. So if these species can't swim large distances, and they can't fly because they're land-based, then if the continents spread apart, how do you find this pattern of fossil remains which are really kind of tightly overlaps and are adjacent from one continent to another. So the Signosaurus, it's a reptile. You know, if you join South America and Africa up, strong kind of fossil records so that these continents were once together. And there's a couple of others. I mean, I'm not a paleontologist, to be honest with you. Yeah, loads of them. I mean, bit of evidence. Choose one that's probably easiest to spell. Glossopteris. It's found in all of the southern continents, and if you were to piece these continents back together, you know, there's a strong kind of pattern where they're found in adjacent continents, right? So Glossopteris could be one, a Mesosaurus. Yep, just choose one for the exam. That's your support. Assess the validity of plate tectonic theory. You kick off with Wegener. What did he say? What did he put forward? How did he prove it? Yep, one bit of evidence, right? Now then, unfortunately, Big Alf didn't know how these continents or land masses, what caused them to move, right? So here we've got Admiral Hess. He was a Princeton geologist. Yep, here he is on his submarine or on his ship. And what did he find? Well, he found that the ocean floor wasn't uniform. All right, the seabed had a series of mid-ocean ridges and mountain ranges, and then at other places you had deep ocean trenches. All right, like the Mariana Trench, for instance, in the Pacific Ocean. How did he find this out? Well, he used sonar, which during the war, you know, the Allies were trying to hunt down German U-boats, and the U-boats were trying to find the Allied ships to blow each other out of the water. And one side effect or consequence of this was, inadvertently, while they were trying to kill each other and blow each other up, they actually mapped the ocean basins. All right, and they realised that, well, number one, we've got mountains and trenches, and at the ridges, or at the mid-ocean ridges, we tend to find volcanoes and earthquakes. Yeah, they call these ridges mid-ocean ridges because they're in the middle of the ocean. Surprise, surprise. So it asked another question, kind of, what is causing these ocean ridges and trenches, these landforms, to actually be there? All right, and Mr. Hess and his other geology friends put forward a few theories. All right, now the first one to try and explain these landforms is seafloor spreading, and here we pop up our picture of a divergent plate boundary. All right, so yeah, they suggested that at the mid-ocean ridges, something is causing magma to rise from the inner earth, and it breaks the surface through the oceanic crust, and it cools when it meets ocean water, and we get underwater mountain ranges, if you like, or ridges. So that was part of the theory. Magma rising, cooling, and we get mid-ocean ridges. Another part of that theory was, what's causing deep ocean trenches? Well, maybe where another plate is being pushed under, just at this point here, you know, the ocean depth, the floor is going to be a lot deeper than it is nearest mid-ocean ridge. You can see where this plate subducts, you've got a far deeper sea trench, if you like. So yeah, it's kind of a pushing and pulling effect. At the mid-ocean ridge, at the divergent plate margin, you're getting ridge push, and at the subduction zone, where one plate subducts under another, you get in slab pull. Alright, but these are all theories that these plates are moving. Again, you've got to prove a theory, so you need evidence. So how did geologists find that evidence? Well, first of all, which one should I show first? Yeah, we'll start with the intro one. So how did they prove that the seafloor was spreading? Alright, first thing is use rock samples. So you can date rocks, range of different techniques, isotopes, carbon dating, I think all that type of jazz. But when they analysed rock samples, you know, the pattern showed that nearer to the mid-ocean ridges, there was younger rocks recently formed. And as you moved away from these mid-ocean ridges outwards, so you get further away from the mid-ocean ridge, the rocks progressively get older. All right, and it's a kind of steady aging, yeah, as you move away. So from younger to older. And if we have a look at a map that shows the let's bring it to the front a minute. The age of these rocks, you can see as mid-ocean ridges are just here, these cracks in the ocean floor. The age of the rock, red is younger and blue is older. So you can see it's a steady kind of aging as you move away from the ridges. Alright, so because it's steady, that implies it's a continuous process of movement. Alright. The other bit of evidence that we can refer to is something called palaeomagnetism. Alright, and palaeomagnetism is quite difficult to explain actually. The definition of it is the study of past changes in the Earth's magnetic field, and the clues that we get to prove that the Earth's magnetic field switches every 400,000 years or so is in rocks, if you like, rock samples. So iron minerals in magma. Obviously, magma is fluid or semi-fluid. It's not a solid. When it breaks the surface of the oceans and cools, it ceases to become a liquid and a fluid, and it sets, all right, and forms crust or rock. Now, what you find is, as you move away from this mid-ocean ridge, you get an alternating kind of pattern that's symmetrical between iron in the rock that faces north and iron that faces south, and it alternates. All right, so we can prove how old the rocks are. They go from younger to older, but we can also prove kind of how often this the speed of the movement as well. All right. Let me see if I put. Here we go. This one. Yeah, this is a better picture. So, evidence for seafloor spreading. Seafloor gets older as you move outward from the ridge, but also the iron alignment in the rock alternates north, south, north, south, north, south, north. And this is kind of like a timeline of the Earth's magnetic field switching between north, or its polarity switching between north and south, right? Super strong evidence to prove that we've got seafloor spreading. All right. Right. Let's have a look at something else. Other evidence, kind of supplementary evidence to support this theory of tectonic plates moving, And remember, why are we learning this in geography? Because we aren't geologists. We aren't kind of inner earth physicists as such. You know, we want to understand why we get tectonic hazards. So we need to take a little bit of a step back, I think, at times, and not get mega bogged down in the science at this level. But other supplementary evidence is at subduction zones where one plate is subducted underneath the other plate. A couple of guys called Wadati and the other one was called Benioff. I think Wadati were Japanese, Benioff was American. Well, what they did is they started to map the magnitude of earthquakes at destructive plate boundaries or at subduction zones, and they found quite an interesting pattern. So nearer the subduction point, where one plate is subducted under another, the magnitude of the earthquakes tends on average to be higher. As you move away, let me get a little, I use my pen today, I don't believe it. As you move away from the plate boundary, the magnitude decreases. And they kind of proved with that, well, this plate that's subducting can't be just subducting flat. Yeah, it must be going in because the focal depth of the earthquakes is getting deeper. All right, so that you can see that pattern, can't you? These are shallow focused earthquakes near the trench. They're higher magnitude because the focal depth is shallower, but as you move and it subducts deeper at an angle, the focal depth of these earthquakes is a lot deeper. So that proves that the plate must be subducting. All right. And the other bit of evidence comes from kind of volcanic chains such as Hawaii. Now, we've got a mantle plume underneath Hawaii and a fixed hotspot where magma rises, a superheated column of magma rises. It breaks the surface, cools, and sets as islands or as rock, like the Hawaiian Islands. And again, we can date these islands. They're all in a line or a chain in a sequence where the youngest is where current volcanic eruptions are happening. So we know that's where the hotspot currently is, but the previous older islands are all in a line. So that tells you that the hotspot is fixed, but the lithosphere, the lithosphere or the crust is moving. All right, so it creates a chain of islands. Right, I'm now going to switch back to a little bit on the kind of inner structure of the Earth, if you like, because this is where the kind of underlying answer to why we get plate movement. This is where we find the underlying reasons. It's all to do with the structure of the Earth. So, like I said, we don't need to get too bogged down into this. You know, we're not studying a course on the inner structure of the Earth, but it's just a bit of background to understand why plates move. So, the inner structure of the Earth. The inner core, solid, very hot. It's all very hot actually, but yeah, even more hot. The outer core is liquid. And then we get the lower mantle, the upper mantle, the asthenosphere, which is kind of where the upper mantle and the lithosphere meet. And then on top of that we get crust. Alright. So basically the composition of the Earth is not the same throughout it. We've got solid bits, liquid bits, honey-like bits, and then on the top of all that we've got the crust. Right. Now, what is causing then these plates to move? Well, quite simply, if we trace it back and we look at the outer core, heat is generated by radioactive decay in the Earth's core, right? So this is the source of the heat. That then goes into the mantle and the asthenosphere. And when you get an imbalance, if you get something that's really hot and something that's cooler, relatively speaking, you're going to get convection, all right? Just like if you've got the heating on in your house and it's lovely and warm, and then somebody opens the front door, yeah, you get movement, don't you? The heat rushes out and the cool air rushes in. It's a similar kind of idea. When you've got a heat gradient, hot, not so hot, then you're going to get movement, all right? So the heat rises through the mantle into the asthenosphere and causes convection currents in the mantle. Now you think you've got a driving force, you've got convection currents underneath this asthenosphere just here, and they're going to be in a cell. Yeah, that force is going to have an effect or move what sits on top. All right, so the lithosphere and the plates and the crust are also going to have a force causing them to move. All right, now a couple of processes that you need to refer to here, so keywords, and they're quite all on this graphic. One, radioactive decay in the Earth's core. Yeah, causes convection currents in the mantle, which causes tectonic plates that sit on top of that asthenosphere to move. Right, simple as that. The processes and their significance, well, as we've looked at earlier, at divergent plate margins, when new crust is formed and the seafloor spreads, this process is called ridge push, all right? And it's where the intrusion of magma into an oceanic ridge pushes the older plates away from the ridge. Seafloor spreading, Mr. Hess, that's what's causing it, ridge push. Your plates float on the convection currents of the asthenosphere, we've just looked at that. So 4 and 2 link. And then finally at your subduction zone, where one plate subducts under the other, this is called slab pull. Slab pull, the cooling slab of the dense oceanic slab sinks into the subduction zone. And if we're going to assess the significance of these two processes, slab pull is responsible for around 80 to 90% of the force. Yeah, ridge push is around 10 to 20%. All right then. So let's keep it simple and link back to why are we actually studying this? Well, we need to have an understanding of what causes volcanoes and earthquakes, and to do that we have got to look a little bit into kind of the structure of the earth and the theories that support that. One last thing, because some of you might be sat there thinking, well, how on earth do we know the structure of the earth without looking at it? And the answer to that is, when an earthquake happens at any point on the Earth's surface, it sends out seismic waves. And there's 3 or 4 different types of seismic waves that cause the ground shaking. Now these waves travel through the inner Earth, all right? However, because these waves have different properties, some of them can only pass through liquid layers, some can pass through solid layers, some can pass through both. So what you get is that the other parts of the world, or some parts of the world, end up where there are no waves detected, and doing a bit of jiggery-pokery and a bit of higher level physics, it proves the composition of the Earth. That's all you need to know. You don't need to worry about this if you, if it seems a bit like mega complicated. P&S waves released through seismic activity. They're recorded at different points around the world. And if we do a bit of jiggery-pokery with physics, what does it prove? It proves that the Earth's structure is not just uniform throughout. You've got a solid inner core, a liquid outer core, and then a mantle as well. Yep. And a solid crust that sits on top of that. And that's how they prove that. Right, step back then. Keep it simple. Here we go. The distribution of volcanoes and earthquakes tend to be near or on plate boundaries. Yep, last lesson. Plate tectonic theory suggests that this is because the plates are moving. So we get volcanoes and earthquakes because of plate movement. 3. The Earth's structure is the cause of the processes that cause the plate movement. So we've got radioactive decay, we've got convection currents in the mantle, ridge push, and subduction. How did we piece it together then through history? That's what we know. What is the kind of path that we followed? Well, Wegener came along, Big Alf, in 1912, and he proves that the continents were once joined together as a supercontinent. They're no longer joined together, so we get continental drift. But he couldn't prove what caused the movement. Along came Admiral Hess, and he proved that the seafloor wasn't uniform, and we had underwater mountains or mid-ocean ridges, and then we had deep-sea trenches away from those ridges. Alright, what causes that, you might ask? Well, can we prove that? Well, yeah, we can, because rock samples and dating those rock samples either side of a divergent plate margin, and palaeomagnetism proves that the seafloor is slowly spreading apart. It's a continual process of spreading. Alright? How do we prove subduction? Well, along came Wadati and his mate Benioff. They mapped the magnitude and the focal depth of earthquakes at subduction zones, and they realised that the higher magnitude ones are more frequently happening at or very close to the boundary, and then gradually as you move away from the plate boundary, the focal depth increases. This proved that the subducting plate is going down, alright, going down into the asthenosphere. And finally, another cherry on top with regards to evidence and proving these theories can be found with volcanic islands such as Hawaii, where you've got fixed hotspots. And where you've got the current hotspot, you get the youngest rock, the youngest islands, but as you move away in a line or in a sequence, you get older islands. This proves the plates are moving slowly, but it also proves kind of the direction and the speed at which they are moving as well. Alright, a lot of stuff in this one, folks. The objective of watching these videos, if you're being mature about them, is not to watch them as quickly as possible for the sake of watching them. Scribble down what you can, because you want to go and do some nonsense other than studying. If it takes you 2 or 3 times to get your head around everything, make good notes, clear things up, ask yourself questions, that's what you should be doing. Yeah, it's time to make mature decisions and take ownership for your learning, rather than just do things for the sake of doing them. Alright, ciao.